All right, welcome back to Weigh the Wrench and another episode of How to Become a Gearhead. I hope you're enjoying the series. Today we're going to delve into what an ignition coil is and how it works and what it does in our car and where it's found and all that good stuff. So, and I have a secret to tell you about ignition coils. All right, so first up, you've been lied to your whole entire life from the auto industry. You don't have an ignition coil. You have a transformer. So, first thing, we gotta learn about transformers. Here we have an example of a step-down transformer. So, on this side, the blue lines represent our primary windings, or our wire on the input side of our transformer. The red lines represent our secondary windings, or our output from our transformer. And both of these are wrapped around a steel armature, which helps amplify the magnetic field and share the magnetic field between the two. So on this side, on our primary windings, we have 10 turns of wire around the steel armature, or 10 coils. And we've also got 100 volts being inputted into it and 1 amp. Now, each one of these coils, and based on how much voltage is coming in, creates a certain amount of electromagnetic field. And that electromagnetic field is also shared equally to this side here. Now, because there is a ratio of 2:1 between the windings, the primary has 10 turns on here, secondary only has 5, there's only so much of that electromagnetic field that can get captured in each one of these coils. So when we kill the power on our primary windings, we cause a collapse of the magnetic field, which acts like a magnet moving by a coil of wire, which induces electricity at a 2:1 ratio. So our 100 volts is now being turned into 50 volts because it's a step-down transformer. And remember, there's an inverse relationship between these two. So the 1 amp now turns into 2 amp. So whenever voltage goes down, amperage goes up. Another way I like to think about energy is that you can't just destroy energy. It doesn't just disappear, it turns into something else. So if we have energy in the form of an electromagnetic field here, and when we cause the collapse of that electromagnetic field, it doesn't just disappear. And so when I teach this, I tell them that that energy has transformed into electrical energy and being induced into the secondary windings. So what's an example of a step-down transformer that we use almost every single day? Well, every single day I gotta charge this thing, well actually probably even almost twice a day, so I need to get my little USB charger. And this is a step-down transformer. We're taking our 120 AC voltage coming from our outlets in our houses, and we are converting it to USB power, which is 5 volts DC. So not only are we stepping down the voltage through the step-down transformer, we're actually converting it as well. So we're turning AC into DC, but that's for a whole other video. So I took one of my old ones apart to see if there's a coil inside. And once you break open the case, you can see there's the USB. And once you get inside there, this part right here is our coils and part of our transformer circuit. So there, see if I can get a good shot in here. You can see, you can literally count the wires. That is going to be our primary, and then underneath is going to be our secondary. And so, step-down transformers and our USB chargers. Okay, here we have an example of a step-up transformer. Same thing's going on though. We've got our primary windings over here, 10 turns on this side, and we've got our secondary windings, except this time we've got 1,000 turns. So the ratio between the primary and secondary has changed. It's now 1:100 ratio. So whatever electromagnetic field the primary windings can create in the steel armature gets shared over here, except because there's so many more turns and coils of wire on this side that we can capture a little bit more of that energy. And so when that electric magnetic field collapses, we get an increase of 100 times. So our 100 volts coming in is now turning into 10,000 volts. But once again, we've got an inverse relationship. So our 1 amp has gone down significantly, and we're down to 0.01 amp. Now that we know how a step-up transformer works, that's an ignition coil. We just have to play around with these numbers and ratios to get what we want. So we know we have a 12-volt battery, but we need to increase that up to 12,000 volts in order for it to have enough pressure or voltage to jump the spark plug gap. So we got to change this ratio to a 1 to 1,000 ratio, which means we got to put 10,000 turns on our secondary windings in order for that to happen. Now that we know a little bit more about transformers, let's take a little road trip and go find some. It's really noisy here, so I'm going to make this really quick, but I'm standing in front of a substation here that uses step step-down transformers. So we take the voltages from our BC hydro plants. They have step-up transformers that jack up the pressure, jack up the voltage to extreme high voltages so that they can shoot at long distances to these substations, and then these substations use step-down transformers to be able to turn the voltage down a little bit, but it still needs to be high enough to get to our homes. And these are the high voltage transmission lines that are coming from our step-up transformer from the power dam going to our local substations, and these have lots and lots of voltage. Once the step-down voltage of about 7,000 to 10,000 volts comes from our substations closer to our home, we still have yet another transformer. This is a residential transformer, and this is going to turn that down to 120 volts, which is what we use inside of our house. Now, note the shape. It's round, it's kind of like a little cylinder, some connections coming out the top, and that's important because that looks like an ignition coil to me. What does an ignition coil look like? Well, this is an ignition coil. Notice it looks a lot like that residential step-down transformer we just looked at. Cylindrical in shape, it's got some contacts on the top, including a bigger one for a spark plug wire to come out. So this is an ignition coil. However, it's from a very old car, so this is kind of like pre-1970, and they were used for quite a long time. So this is what an ignition coil looks like. But so is this, and so is this. They're just different, and different time frames of when they went onto cars, and for good reasons, which we'll get into later. We just learned that this is an ignition coil, but it's actually just an automotive name for a step-up transformer. So really we're learning about what a step-up transformer is and why we need it on our car. We need to have a step-up transformer because 12 volts coming from our battery is not enough to jump the gap on our spark plug and ignite our power stroke. We need to have way higher voltage, upwards of 10 to 20,000 volts. All right, so here we have a spark plug, which we're going to talk about in future videos, but this little guy is basically responsible for taking our voltage, running down the center of it, and jumping a gap right here, called our spark plug gap, getting to the ground electrode, which is this guy on the end, which is connected to the engine, and goes back to the negative side of the battery. We need to make a spark in here for our power stroke to ignite our air-fuel mixture. But if I have 12.8 volts here, so I'm simulating a battery, and I put the positive terminal on there, and I put the negative on the case, you can see that there's just not enough voltage, not enough pressure to actually get the electricity or the electrons to jump that gap and make a spark for us. So now if I take my power supply, which is 12 volts, and I put it through an ignition coil, which is now what we know as a step-up transformer, we're going to get 15,000, 20,000 volts coming through and jumping our spark plug gap. All right, so we've got our power supply set to 12.7 volts, simulating battery. We've got our ignition coil, and on the top of the ignition coil are two connections. They're actually stamped on the top, so one's got a little negative symbol. That's where I've put my negative of my power supply, and on the positive would be power from the ignition switch. But in this case, I'm just going to basically tap it and act it like a button. And then on the top is our high tension wire going to our spark plug or to our distributor. And right here, I've just put in a paper clip, so I've got a little metal pathway with a little gap here between the negative terminal, and now you should be able to see this spark. And I'm going to zoom in on this too. So not only can you see that that's a pretty big gap, we're talking about almost 1/4 of an inch gap, and we're getting electricity to be able to jump that. And so we're upwards of 15,000 to 20,000 volts. Now, keep in mind, this is a great way to test an ignition coil too. If you can get that high tension spark to work, then it's not your coil that's the problem. Another thing with these ignition coils is these are actually filled with oil because when we put electricity through that coil of wire, we're actually making a little bit of heat, you know, just like a little wire in a light bulb. And if we let that heat get too much, then we'd have some internal damage. So they're filled with oil to help dissipate that heat. Now, if you had one of these ignition coils in your car and a distributor with points, you also had one of these guys, and this is called a ballast resistor. And this was simply mounted to the firewall, and what it did was when you turned the ignition key to start your car, it allowed full voltage and full current to go to your ignition system, making a really nice healthy spark and get your car going. But once your car was going, it didn't quite need as much amperage, and so this resistor would use up some of it, and limit how much was going to the coil. And this lengthened the life expectancy for your coil and for your points. All right, so here's an ignition coil that I had sitting around the shop. You can see there's our metal armature that sits around, and inside is our coils of wires. Now this one I actually cut so that we could actually see this. So when you're looking at this, these guys right here, you can actually almost count those little copper wires in there. So, and there's not that many of them. So this is going to be our primary windings, maybe in the couple hundred range of coils. And then right here is our secondary coils. Now you can see there's quite a bit more of them. The wire is so fine that you can't actually even see the diameter of it, and there's way more wraps on it. We're talking thousands more. And so this is going to be our secondary windings. And so once we get electricity through our primary windings and we make a magnetic field around this metal or steel armature, we make a magnetic field, and that magnetic field saturates the secondary windings as well. And when something triggers the voltage or the current to stop flowing in our primary circuit, we get a sudden loss of our magnetic field, which kind of acts like a magnet passing by the coil of wires. And Faraday's law, we have some amperage induced into the secondary windings. Now, there's a ratio between the two, and that ratio determines how much it steps up or steps down. And in this case, it's way more, so we're going to get a step up in our voltage, and then the only spot for that voltage to go is on our high tension post here, which is going to go to our spark plug wires. Back to our original style ignition coil. So the time that it would take for electricity to flow through the coil of wires, make a magnetic field, have it saturate the secondary windings, have it triggered to collapse, induce some amperage, and send it high voltage to a spark plug takes a certain amount of time. And you got to remember that these were usually used on old V8 engines, and so that had to build yet another one for another cylinder and another one for another cylinder in rapid succession. And so it had very limited time. Introducing coil packs. So the year is now 1970s and 80s, and automotive engineers are experimenting with all kinds of stuff, including ignition coils. And some smart engineer started thinking about, you know, this ignition coil is not bad, but it starts to have problems because it doesn't have a lot of time to build up its magnetic field and have it collapse because it's running for V8 and 8 cylinders. Is there some way that we could fix that? Well, why not make more of the coils? So the coil packs, the way they worked, if you had this kind of system on a V8 engine, you now had 4 times the length of time that it needed to build up a magnetic field before it had to collapse again. So what that did is it made sure that you had a really good spark with a big high voltage instead of having to rush it doing its job. Now, if you notice, these coil packs have 2 of these high tension leads coming off of it. And so what would happen here, for example, this one here, cylinder 2, when this one's getting its spark for the power stroke to happen inside that cylinder, cylinder 3 would also be getting the spark at the same time. So it would always shoot out of both at the same time. And cylinder 3, the way they designed it, would be getting this in an exhaust stroke where if there was a spark, it wouldn't do anything at all. In fact, it was wasted, and that's what that's called, the waste spark. And pretty quickly after that, they decided, yeah, if coil packs made an improvement in making a better spark because there was more time given for that magnetic field to grow and to saturate, then why don't we just make a coil for every single cylinder? And introducing coil over plugs. It's called a coil over plug because our coil is now up here at the top of the motor. We've got this part here, which is now replacing our spark plug wires. And at the very end, that's where our spark plug would go into inside of our motor. So, coil over plug. Now, if you had a V8 engine with coil over plugs, you now have 8 times the length of time for that coil to make a magnetic field and make a nice powerful spark so that we always have a spark at our spark plug and we have less misfires. Now, the other beauty thing about coil over plugs is we have now eliminated the need for spark plug wires, which is a maintenance item. These last a couple of years before they start giving you grief and they start to break down and degrade and start causing misfires. So without these things flexing and sitting on exhaust manifolds and getting pinched and wet all the time, this right here replaces the spark plug wire. All 3 of these ignition coils are going to need something to trigger the cause of the collapse of the magnetic field inside, but that's going to be a whole other video on distributors in the future. But for right now, if you got a coil like this on an old car, you're going to have some kind of mechanical distributor that's going to cause that collapse. But on these guys here, we start to enter an age and a year where computers are starting to get into cars, and we can use computers to trigger that collapse or send pulses to these ignition coils for that to happen. Right, and here we have yet another ignition coil. This one's off a small engine, and now it's off of a magneto ignition system. But the same stuff's going on here. So we've got primary and secondary windings wrapped up in here around a steel armature. We've got a high tension spark plug lead coming off of our secondary. The only thing different is what's causing the triggering of building of our magnetic field and what's collapsing it. And so on our flywheel on our small engine, this is attached to our crankshaft, when the motor's spinning, there's a magnet on the outside here of the flywheel, and every time that magnet goes by the coil of wires, we get a buildup of a magnetic field, and then as soon as that magnet leaves, we get an instant collapse of that magnetic field, and then we get that voltage stepped up and shot down our high tension lead to our spark plug. And in perfect timing, because this flywheel is actually keyed to the crankshaft, so that spark happens at a very exact time. So how do we test these guys? Well, there's a whole bunch of different ways. One, you could test it while it's on the car, while it's actually running. And then there's something called bench testing, where you can take a part out of a car and take a multimeter, take power supplies, and test it outside of the vehicle. So let's start on that. So remember, our ignition coil is a step-up transformer, and we have a wire inside that makes up our primary windings, and we have a wire inside that makes up our secondary windings. And you can measure the resistance of a wire to be able to tell if it's got a short in it, where the wire has broken through and touching somewhere where it's not supposed to, or whether there is a complete break in the circuit and electrons can't get through the circuit. So what we're going to do that is grab your multimeter, have it set to very low ohms, so where the omega symbol is, for checking primary. Because we have only a certain amount of loops and there's not that many wire, when you check from one end to one end, you should get a very low ohms, probably something under 5 or 6 ohms. And then on the secondary side, when you put it on the secondary side of the wires, because there's so many more turns on here, there's the longer the wire gets, the more resistance it has. So we're looking upwards of 5,000 to 8,000 ohms. If you're a cool dude and you got yourself a muscle car, then you're going to have one of these style ignition coils. And the plus and negative terminals on your coil is your primary windings. So it goes from the positive, makes coil a loop, and then comes back up. So set your multimeter to something very low, like 200 ohms, because this resistance shouldn't be very much because there's not a lot of windings. So in this case, we're getting about 4 ohms, so that's good. Now the secondary side, one end is connected to the positive terminal, goes through, makes a whole bunch of wraps, and then comes out the second center post for our spark plug. So put one end down in, make sure you're touching the metal, and then touch the end of the positive. Now, check this out. See how it didn't move? Now, that doesn't mean it's not good. It means that it's over the limit of what I've set the meter at, which is really important because it looks like it's not good. So, if I bump this up and go to the 20,000, you can see that it was just over the limit, so that's why I was displaying a 1. So this one is just about 9,000 ohms, and that's because the secondary windings have way more wire in there. The longer wire is, the more resistance. So this is a good coil. Put her back in your 68 Firebird and you're good to go. Alright, if you have yourself a new car, you're going to have a coilover plug set up, but you can do the same checks. So primary windings, for testing those, you're going to find it on the connector here. Now you might have to Google up for your individual car which pin out is which, but if you've only got a couple, through process of elimination you can figure it out. So remember, primary windings, we are looking for pretty minimal resistances, but this is a bad coilover plug because I pulled it out of a vehicle and it's got 1,500 ohms of resistance in the primary, so that's not a very good sign. Now, the secondary checks, you're going to have one of these pins and the other end is going to be down where the spark plug would sit. Now, make sure that you actually are getting down to the metal contact, so if you need to, get a paper clip or a screwdriver and make sure that that's connected to the metal at the bottom. Now, also, remember your multimeter, so crank it up to make sure that you're not missing a reading because it's just going over limit. Now, in this case, I do all 3 terminals and I'm not getting a single thing. So that tells me there's a break in the wire for the secondary windings, and this is a no good coilover plug, and I know that because I removed it out of a vehicle. And if you got a coil pack, that means you got a car in the late 70s or 80s and you need a new car. That thing's gross. But if you do want to check it because you're having some issues, primary windings, once again, are going to be down on these connectors. You just have to figure out which terminals to check. And your secondary windings are going to be the shared spark plug terminals for each coil. So for example, cylinders 2 and 3, remember, secondary windings, we're looking for higher resistance, so this is 5,500 ohms, and each coil pack should pretty much be the same and according to your specifications for your vehicle. Your next tip on how to become a gearhead is don't let these plastic covers deceive you. Vehicle manufacturers put these on to pretty up the engine bay so when you pop the hood it looks nice, or to hide everything important underneath so that you feel like you can't do anything. You pop the hood, you open it up, and you see plastic all through here, and you have no idea what's going on, and you don't even want to attempt it because you can't find screw holes, etc. So don't worry, keep the covers off, learn how to do that, and then underneath everything is good. So let's take this cover off so we can see what's going on underneath. Another tool tip that I learned a long time ago from my old mechanics teacher, John Laquette, is you always grab an extension, even if you don't think you need it. The reason why is you got a short little socket on your socket wrench, and when you're trying to free up a bolt and it all of a sudden gives, you're going to wrap your finger across something and get cut up badly. Whereas if you have an extension, now your hands are well away from the motor and no problems. So now that I've got the cover off, I can see that I've got 4 coilover plugs here. Now, if I thought one of my coils was bad and I'm not getting a spark for one of my cylinders, I could do something called a power balance test. And the engine has a certain RPM and it runs a certain way, nice and smooth, when all 4 cylinders are running. Now, if I disconnect the electricity going to that coilover plug, then I'm not going to get a spark or a power stroke in that cylinder, and that makes the engine run rough if it was working properly before. So when I disconnect it, if there's a change in the RPM or a change in the vibration of the motor that I can hear, then I know that the coil was working. If I disconnect it and there's absolutely no change, then there's a good chance that it's a bad coil and it wasn't working before, and when I unplug it, it's still not working. So let's do that test now. Alright, engine's running and I got my cell phone camera filming the RPM, so I'll probably splice the two together while I do this. So, first cylinder's up. Okay, it's running way rougher. We're going to see that RPM drop. It's only a 4 cylinders, so it changes quite a bit. If it's a V6 or V8, then it's not so much, but you'll still feel it. RPMs are back, so then that means that was a good coilover plug, or there's a spark happening. Right? Okay, second cylinder. Alright, same thing, engine's running rough. Okay, put it back on, it's back to normal. Same thing with the third. And same thing with the last one. Now with me disconnecting those terminals, I might have popped the check engine light, which we'll talk about in a bit. Now our last video we learned about Faraday's law and how when electricity goes through a coil of wire we get a magnetic field, and it can work in the reverse, right? So if we have a magnet and we run it by a coil of wires, we can induce electricity. Well, this is a tool that uses that theory. So this is a coilover plug tester, and essentially what happens is we've got a little coil of wires here, and you're supposed to put this probe right next to the part you're checking, and it basically senses the magnetic field that's there, and when it collapses in the tool coil, it shoots down, induces some electricity, and tells the meter what's going on. So this coilover plug tester is a really simple tool to be able to check coilover plugs, whether they're good or bad, or they're weaker or stronger than others, etc. And really they should just all be the same reading if it's a good setup. So let's test that now. I'll show you how that works. Alright, so pretty simple, easy machine to use. You just basically turn it on, change the function to make sure it says COP for coilover plug, and we want it on 4 cycles, and we'll make sure we're capturing kilovolts, and we're capturing the maximum and minimum. So now all we got to do is put it over the coilover plugs. So this cylinder here is getting about 11,000 volts. Cylinder 2 is getting about the same. Cylinder 3 about the same, and last cylinder is about the same as well. Now, if I was getting no reading off of one of these coilover plugs, then that would give me some info to look into that specific coilover plug, or if I found that one of them was way lower than the others. And so once I've checked all of these coilover plugs and maybe found the problem, remember I'm also going to refer to my OBD2 scan tool and see what's happening there. If I'm getting signs that, you know, cylinder 3 here is having a misfire, and when I do this test, the coilover plug tester is telling me it's got an issue, then that's kind of confirming my problem, and maybe I'd go on to a bench test just to double check. Now, a thing to note here, we are learning about ignition coils and not the whole car all at once. So any situation where there's no electricity getting to the coil will also simulate that your coil is not working as well. So if you take out an ignition coil and it bench tests okay, then it's also probably the next step to start looking at, are you getting positive and grounds and signal from your connector here. Could be a chewed up wire from a rat, could be a loose connection, etc. So check that stuff as well. Do you remember when I disconnected the connectors at the coilover plugs to do our power balance test? Well, that has popped a check engine light and it's showing up on my dash. So I know that's what the code's going to be, so I just need to clear them. And that's where we get into our next tool that you should have if you want to be a gearhead. So this is a OBD2 scan tool. It works on vehicles 1996 and newer, and you can use this to read what the code is. It gives you a hint on how to fix the problem, which in my opinion has made fixing cars even easier these days. And once you fix the problem, you can clear the code and get rid of that check engine light. So we're going to do that right now. Alright, so now that I've gotten in here, you can see all my readiness monitors are okay. And I have one of 14 codes, so I've got 14 codes here. Now, I know I had no check engine lights before I did the power balance test with you guys, so I'd be tempted to just clear all of this. But remember, this is a tool to help you fix these problems. So if you were having a check engine light and you got your scan tool out and it popped some of these codes up and it all kind of referred to your ignition coil, then you can start doing your testing that way like we just talked about. So it helps you narrow down the problem rather quickly. So I'm going to find that a lot of these are repeated, but here's an example. So ignition coil A, primary secondary circuit issue, primary coil B, coil C, and I'm probably going to have a coil D, right? And so a lot of these will be circuit problems, coil problems, just repeated. That's why there's 14 codes. So I'm going to quickly scroll through this, but I'm pretty sure it's just going to be all these coil codes that I'm going to be able to just delete. So I'm going to go clear these now. Go to erase codes. It's going to ask me, am I sure? And codes are cleared. So there is our check engine light. Just looks like a silhouette of an engine here, and if you've ever got your car running and you've got this on, then that's your check engine light, and the computer has figured something's wrong with your car and it needs to be looked into. We're going to make another video on scan tools pretty soon, but for right now, that's my check engine light, what it looked like with the car running. And now that I've deleted the code, when I start the car, this thing should go away. Woohoo! Problem fixed. Money saved. Another diagnostic strategy that you can use with coilover plugs is the fact that all of the cylinders have the same coilover plug. So if you have a suspected bad one, you can actually swap positions with a neighboring coilover plug. And when you use your scan tool and look for the check engine lights, if you notice that the misfire has now jumped to the neighboring cylinder, then you know that that was a bad coil because you've moved it over to that cylinder. Bam! There's another video from Way of the Wrench on how to become a gearhead. This time we just finished up a video on ignition coils. So hopefully you learned a lot about these guys and can now start to do some more work on your cars. And I think by now, a couple episodes in, you guys should start to feel the oil and gas starting to course through your veins, and every time you touch a car, you're getting more and more confident about it, which is really cool and what this whole series is about. So if you're enjoying the content, I would love a like and a subscribe, and till next time, take it easy.